Hi, my name is Juan Pablo Serrano, and today I'll be presenting on the topic of linear programming for the course COP 5531, also known as Advanced Algorithm Design and Analysis, lectured by Dr. Okusan Topsico at Florida Polytechnic University. First, we should start with the definition of what linear programming is, and it is easily more understood by an optimization technique for a system of linear constraint and a linear objective function. That it is defined by quantity and its goal is to just optimize it into a linear program. It is better understood as just like a simple technique where we are trying to depict complex relationships through linear functions and then just find their optimum points and vertices. The important word here is like depict, because what we're trying to do is to find these real relationships that might be much more complex to help us simplify them to a linear relationship so that we can understand them better, so we can like model it and see how it actually like relates and work with it. Now, the applications of these linear programming problems are literally everywhere, from our day-to-day normal life to our professional fronts. So when we are going from work to home and we are trying to get the shortest route, at that moment we're implementing linear programming, because we are minimizing, we're being cost efficient, we're like having constraints about like taking this route, about taking this U-turn, minimizing times and things like that. There are definitely like for project deliveries or due dates when we want to like be on time and make our team work as much efficiently as they can so that everything's done by the due date, like all the strategies used in between. That's linear programming. And it is better understood by this simple problem. Here we have so let's say this FedEx delivery person, that it is at point A, the warehouse, has 6 different destinations, U, V, W, X, and Y, and Z. And the numbers on these lines indicate the distance between these points. To save fuel and time on delivery, the person wants to take the shortest route. So this is like the most basic linear programming application. And what we can understand here in the pic is that the delivery person will calculate the different routes for going to all the different destinations and then come up with like the shortest one. Coming up with the shortest one is what we call linear programming. Now, for this specific case, the objective of the delivery person is to deliver its parcel on time at the 6 different destinations, and this same process of choosing the best route is called operation research. In the part of operation research, we'll like explain what it is better, but the operation research here is to make the FedEx delivery guy know where he has to go and like take all this decision making and set of methods for him to put this system that will be the delivery model that will work for him, that will eventually give him a shortest route for him to use. Now, in linear programming, we use for like obtaining the model of most optimal solution for a problem with the given constraints. And now in this linear programming, we will formulate our real life problem into mathematical problem, which involves objective function, linear inequalities that are subject to constraints. Most of the times it will be like less or equal than a certain amount, because it will like have to meet it or be more than it for it to like work, for it to fit into this linear programming modeling that we are creating for the problem. Into defining going back to here, we will drastically need to understand that yes, this could be implemented into a real life situation, because we can represent it as a oversimplification of a real route, but we are not taking like straight lines. We have to take U-turns, we have to take intersections, we have to respect signals, and we cannot just fly all over traffic jams. So there are so many different things, but there's just like this simple assumption that we have reduced the complexity of like a problem drastically so that we can just like have a better understanding of it. Like that's what basically linear programming is. So we can like create all these different scenarios and like where would it work best, and like how can we like not get lost with it, because it would be like in such a big spectrum where we have like all of these different things that we have to like take care of them and like follow the line, continue with the string, not just get lost. The common terminologies that we used when solving linear programming problems, as talked in like the problem before, we're gonna define them, because for the next problem we're gonna have a better and clearer idea on like how to solve a linear programming problem. So first of all, we need to take into consideration the decision variables, which is like the operation research, basically what we mentioned before. We set these variables as u, v, w, x, y, and z, and we try and represent it as the ultimate solution for our problem. Then there's the objective function, which is what is defined towards the decision making. What will like all of this set of rules, how will they give us this answer? Of course, the constraints, which are like the limitations of our problems, and non-negativity restrictions, which for all linear programs that we're going to be encountering, this is like the decision variable that should always take a non-negative values. So meaning for all these decisions should be greater than or equal to 0. We'll encounter this in the problem ahead, which is the simplified diet problem, a very known problem in linear programming, historically known because it takes all that's linear programming in one simple task, which is follow a diet and meet its minimum nutritional requirements. But it has like the constraint, meaning that it will be x has to be greater or equal than 0, because it won't work, like it won't fit on the margin, like its vertex won't be linear, like it won't be linear, like this non-negativity restriction would mean that the whole other spectrum of the problem satisfies. I'll explain myself better as we go through it, but yes, there are steps for solving linear programming problems. Every time we encounter them, it is better if we approach these 4 simple techniques, which is first, we just identify the decision variables. Second, we write our objective functions. For a third, we would just mention its constraint. And for a fourth, we would explicitly state the non-negativity restriction. And as our final step would be to just outline a resume of like everything that happened in our linear programming problem, so that we just have like a clearer view and a better understanding of it whatsoever. Starting with the simplified diet problem, it is first to just go ahead and know what the goal of this problem is. Like, what do we want to solve out of this thing that we're encountering? So the goal is to minimize the cost of food, the price that we're wasting on the monetary value that we're spending on money. And there is our first constraint, that is but meet the minimum daily nutrition requirement. And here is where it is asking us to eat, where it is telling us to meet a nutrition requirement, to feed ourselves, to not just opt out of the problem and be like, I'm not going to eat, and that's how I'm going to minimize the cost of food. It cannot happen. Like, we need to create this diet, and I'm going to show you a simplified method, or where we are going to follow a set of rules and put them in a very specific order in order for us to like have a clearer understanding of this problem whatsoever. But we have these two different values, which are our food depicted as our apples, bananas, carrots, dates, and eggs. These were chosen specifically because they follow A, B, C, D, E variables. So when we put them in our chart, we can just go ahead and name them as A, B, C, D, E. Also, when we are placing them in, we're going to have to put each in a linear system, in a linear equation with its respective values, because these will be considered constraints for them to like go hand and work with the nutritions, because that is like the whole spectrum of the problem, for the food to meet the nutrition requirement and for it to work for the person. Following up, I've scanned what I worked in my notebook with the diet problem, but the table that you guys see on the corner is the data that I've received from Penn State University. And this is the data that we're going to be working with. But we see that for now with this table that we have a 2-dimension, but that minimum daily requirement, it's what makes it be a 3rd-dimensional problem, and I'll explain it at the end. But for now, what we can understand is from the table that we have, we go ahead and we set our variables, and having our variables, this would help us know how much is the minimum daily requirement corresponding to that variable, and that whole calculation would be a cost function that would just add everything up and give us this value. So the constraints for our problem are depicted as protein, the vitamin C, iron, and this other, that X has to be greater or equal to 0. And this is the non-restrictive constriction that we saw that there is always in a nonlinear, that we always encounter at nonlinear problems. The simple version to solve this is that we only eat apple and bananas, because we only take A and B as our variables, and we put it in our C cost function, and we put it in our C cost function, and then we put each one of it in our constraints, and we would just have A and B would be greater than or equal than 70, greater than or equal than 50, greater or equal than 12, and it just being greater or equal than 0. These will be our different constraints, and we would study the case from it. We will move along from just setting it like in a different set of steps and then going on ahead and graph it. So the graphing part is where we put all the practices in work, because it's where we see and where we study and where we minimize. Because when we graph it is when we are taking out the slope, and the slope is what gives us where this linear function is going to be and whether it will be accepted or not, where it will satisfy our problem or it won't. And in our graph methods, let's just see the first one, which is C4. It is like it covers the whole area, because X just has to be greater than 0, and it starts from 0 to like the whole expansion. Now we go ahead and we go to C1, and we see that there's this linear stated on point B, which is 58.3, and on point A, 175. So from these two, like, it has to be greater than that, because it cannot be leaning towards the line, because if it is leaning towards the line, it is meaning that it will like be decreasing, and
it will just not, it won't satisfy it. Like, it will just won't be feasible for us to have like this solution in our linear programming problem. Same thing goes for C2, same thing goes for C3. What we have just done in here is taken the 70 and dividing it with the value of A with the in the constraints, and that's how we get the value of M. That helps us understand more the graph, help us know more about like how is this linear program being affected by this change, and will it work or will it not work. And after we finish knowing how it will be with each constriction, we put it all in one graph, which is the graph that says that it satisfies from C1 to C4 and that it is a feasible region for every constraint to function. We see that from A to B, there are definitely just too many bananas. And I will tell you how this is translated to too many bananas. But this is basically by just adding contour lines to our graph. So by adding these contour graphs, that would be these constraints that we are just putting them in this scenario to see if it will work and to see what we need to do and what would happen. It's just in order for us to have a better understanding and be able to read and work with the problem. Like as how we see in the last part of us solving the problem, where we can see that K definitely just continues to increase, and where A, which is apples, is 0, the cost will be 583 cents, which is $5.83. For 0 bananas, like this is just like the minimum. This is the minimum. And here we can easily just read it by looking at the graph, where the line is at the minimum 58.3 and it goes all the way up to 175 in A. So we see how K has increased through every one of these lines for it to be accepted for all the other constraints. We see how it reaches its limit at the minimum for the function of the cost of F, A, and B, and its minimum would just be $5.83 spent in bananas for it to meet the minimum requirement of the diet. And K, which is our constant, would end up being 80, and our slope for this final graph would be -8/10, which satisfies the condition that we're implying. And it translates that our diet is based on too many bananas. We can definitely have some final observations, and this is what I meant by just having a resume of what happened through our problem. And first of all, we see that our constraints are linear. So if it would take us to another dimension, if it would be a square, we would definitely have approached this problem in another way, and it would just be quadratic, and like it would be in another dimension, and many different like variables would change. The constraints would be like more difficult too, but it is possible, but not for this problem. The cost function is linear and affine, and by this we mean that we're just allowing and preserving the parallel relationships that it has throughout the problem. So like the protein is related to like the chart value, and how this like can depict you this value, and how this like linear system like function can depict you this. Like that's what we mean by affine. And two variables, which is feasible solution, like having a feasible solution, just being able to understand the problem and something that makes sense solves it. as a last, the minimal value is reached, which was 58.3, 5.83, and we can see it at the corner vertex of the graph where it's like the letter B, and there should be a point indicating that this is like this corner vertex that sets this satisfying standard limit for our linear programming problem. Thank you.